Hello, my name is Drew McCready. I'm with Vitatech Electromagnetics, and we're here today to discuss active field cancellation systems. This one in particular is made by Stefan Meyer, who is a German supplier of active cancellation systems. This is a very good system we use extensively here in the United States. We're also going to be discussing passive magnetic shielding, and we're going to discuss how these two systems can interact to improve cancellation of magnetic fields. First of all, we're going to discuss the active field cancellation system. We currently have a field source in this white box behind me. It's a coil. This field source produces an AC magnetic field that extends out into this volume of this field cancellation system. This active source produces a high field on the right-hand side and a lower field on the left-hand side. This active cancellation system has a set of Helmholtz coils. The Helmholtz coils are pairs of coils. The Helmholtz coils maintain a uniform field within the space between the coils. In this particular case, we have a y-axis coils, which are on the left and the right, an x-axis coil, which is in the front and the back, and a z-axis coil, which is in the upper and lower part. In this particular case, in this system, the z-axis coils are in the middle in this central part. Now, right now, with this active field source, you can see that on the display that we have a very high y-axis field that is going from this right-hand side to the left-hand side of this cancellation system. Right now, on the right-hand side, next to this sensor, this first sensor, we have 25 milligauss RMS of magnetic flux density. At the left-hand side, we have approximately 2.5 milligauss of magnetic flux density. So in this particular case, the magnetic fields from this coil decline at the cube of the distance. So we have an order of magnitude of difference between the first sensor and the second sensor. Now, this is a slight exaggeration on what you would normally find in the field, but it's not unusual to have AC sources of magnetic fields that are close to your sensitive magnetic equipment. In this particular case, we have over 20 milligauss of difference between the one side and the other side of the cage, this cancellation cage. And in many cases, this amount of difference would cause severe problems with any equipment that you were operating, any magnetically sensitive equipment. Now, what I will be doing is I will be turning on the Stefan Meyer ACS system so that it's able to cancel these AC fields. Now, first of all, the Stefan Meyer has a set of controls on the front that allow you to turn on the each individual channel, X, Y, or Z, and it also allows you to turn on individual AC, DC, or both AC and DC cancellation. In this particular case, I'm going to turn on all three axes, and I'm going to make it AC and DC cancellation. Okay, I've turned on the cancellation system, and it is now canceling to the very center of the cage. If you look at the left-hand side of the screen, you will see that there's a sinusoidal waveform. This is the uncanceled field from the field cancellation system. If I turn on the ACS system, you will see that that waveform goes to a flat line, meaning that the field is canceled in the center of the field cancellation system. Unfortunately, we still have significant fields on the left-hand side and the right-hand side. In this particular case, we went from 25 milligauss to 18 milligauss. So we still have a substantial field on the right-hand side, but it has been reduced. If we go to the left-hand side, we had 2.5 milligauss. We now have 4.4 milligauss. So the field is actually increased on the left-hand side. And this increase is due to overcompensation. The amount of field is actually being set to cancel the field in the center of the cage, and it's actually overcompensating for the field on the left-hand side. The Steffenmeyer active cancellation system that we use has many great features. One of the best features is its ability to recover from an overload. This feature is very important, particularly for electron beam equipment like electron microscopes that employ magnetic lenses. This system can recover very fast from a severe overload. I'm going to mimic the overload using this high-powered magnet, and I'm going to wave it in front of the sensors. This magnet is way more powerful than you would normally have with an electron microscope. If you look carefully at the screen, you'll see that the system is perturbed when you move the magnet in front of it, but it quickly recovers after the magnet is removed. Hello, we're going to discuss passive shielding and its effect on the magnetic field inside this enclosed area. Right now we have 25 milligauss on the right-hand side of this area, and we have 2.5 milligauss on the left-hand side. We're going to start with two ferromagnetic materials. The first ferromagnetic material is mu metal. This is a high permeability, very strongly magnetic or anti-magnetic, in this particular case, material that's very effective, but it's also extremely expensive. This one thin piece of metal, which is less than 1/16 of an inch thick, is over $400 for this one 3-foot piece of material. We're also going to use another material, ferromagnetic material, which is silicon steel. Silicon steel is a common type of steel that's used in transformers and other electrical applications. This material is not as powerfully ferromagnetic as mu metal, but it is considerably less expensive, and it is weldable and formable, where mu metal, if you were to bend it or hammer it or screw it or drill it, would need to be annealed in a hydrogen furnace to retain its magnetic properties. Okay, these first two materials are ferromagnetic materials. We're also going to be exploring the use of highly conductive materials. In this case, this is aluminum. It's 1100 grade aluminum, which is a very highly conductive aluminum because it is almost pure aluminum. Other conductive materials can be used, but we at Vitatech have found that aluminum is the easiest to use and the most cost-effective material. Okay, first of all, we're going to try the mu metal in front of the enclosure. So we've slid the mu metal in front of our magnetic field source, our coil, and you can see that we've dropped our magnetic field from 25 milligauss to 8.5 approximately milligauss in the first sensor, and the second sensor is 1.8 milligauss, about 2 milligauss. So we've decreased our magnetic field with the mu metal material, but it hasn't decreased greatly, and particularly at the far extent, we haven't decreased significantly. We've only gone from 2.5 to 1.8, so it's not a significant reduction in the magnetic fields. Okay, let's try the silicon steel. The silicon steel, as we stated, is less expensive. It's heavier, but it's still very effective, and in fact, it's more effective in this particular situation. We're now going from 25 milligauss to 6.5 milligauss, or 6.25 milligauss, and on this side, on the outside, we're about 1.3 milligauss. So we've decreased the fields more substantially than we did with the mu metal. So these type of materials are both ferromagnetic materials. These ferromagnetic materials, if we work by flux ducting, What that means is that the magnetic fields enter the material and flow almost like water through the metal and then come out the ends of the material and flow around. So it is similar as again to water flowing through a pipe. It flows through the material out to the edge and then comes out of the edge of the material. This type of flux ducting works best, of course, if you have it surrounding the entire enclosure, so it flows completely around the enclosure. Another aspect of these materials is that they change, these conditions change as you apply more and less magnetic fields. The materials become saturated, and as particularly mu metal can become saturated at very low levels, and in fact is probably being saturated in this experiment right now. Last but not least, we have our highly conductive aluminum. And we insert this in front of our source. It will reduce the fields, in this particular case, to 4.5 milligauss from 25 milligauss. So the aluminum has the highest amount of attenuation of the two materials that we just used. Not only that, if you look at the far sensor, we went from 2.5 milligauss down to 0.5 milligauss. So we had a greater reduction on the far sensor than we did with the other materials. And the primary reason for this is that the aluminum works by a different technique than the mu metal and the silicon steel. It doesn't work by flux ducting, it works by canceling the magnetic field due to eddy currents that form in the highly conductive aluminum. These eddy currents are created from the magnetic field going into the material perpendicular to the field, and these fields set up strong currents flowing through the aluminum material. These strong currents produce an equal but opposite field being generated inside the aluminum, or almost equal. This field then cancels the effect of the source field and opposes the field. This technique produces very consistent results, and as you can see in this particular case, superior results than the mu metal or the ferromagnetic silicon steel. If we apply all three materials, we can increase the attenuation and reduce our magnetic fields even more than with each one individually. In this case, we've reduced the field closest to the sensor, originally 25 milligauss, all the way down to only a little over 1 milligauss. And the one on the far side is down to below 0.3 milligauss. So we've effectively created a much lower field in this region. And it's not only that, it's a fairly uniform field. We have only about 0.7 to 0.8 milligauss of variation from one side of the enclosure to the other. When we combine our shielding with our ACS system, we can achieve the best results. And in this particular case, when we use our shielding material along with the ACS, we're able to achieve stellar results in terms of our magnetic field. We're able to reduce the field to 0.4 milligauss across this entire region. It will be canceled, so we have 0.4 here, 0 milligauss, 0.4 milligauss. So we've decreased our range of flux density tremendously, and we have achieved superior results.